Hi everyone. So in this video, we're going to put together some of the things that we talked about in the last two videos. So 2 videos ago, we learned what the domain of a function is, right? We learned that the domain of a function is the set of all values that you're allowed to input into the function. And so we talked about how there are certain things that can arise that make your function undefined, right? So the big 2 were dividing by 0 and taking the square root of a negative number. So we kind of talked about how we could look at a function and use those kind of situations to figure out what numbers are and are not in the domain of the function. In the next video, we talked about what's called interval notation. So we basically learned a more formal way of describing a set of numbers. And so in this video, we're just going to kind of put those 2 ideas together and basically take a function, figure out what the domain is, and then express that domain in interval notation. We're going to get into some examples that are a little bit trickier than the ones that we've done so far, so just kind of heads up on that. And this video is just going to basically just be examples, lots of examples. And I think the examples will get a little harder as we go, is kind of the general trend. And I would recommend that for sure in this video, after the first example or two, try pausing the video and trying some of these examples yourself. I think that you will find, this video a lot more engaging if you actually pause and take the time to try these things out yourself. Okay, so I want to jump straight into an example. And for this first example, I'm going to kind of break down the steps that are involved. And then once we have those steps established, in the future problems, we'll kind of just jump straight into it. So in this problem, we're going to find the domain of the function f of x is equal to 2x over 3x minus 5. Okay, so the first thing you always want to think about when you're finding the domain of a function is remember that the domain is the set of x values, or whatever your input variable is, the set of inputs such that the function is defined. And so usually you kind of want to work backwards and first start by focusing on, what would make this function undefined? So that's what I'm going to kind of write down as our first step here. So the first step is to identify the situation that would make this function undefined. And so that's going to vary, right, depending on what your function looks like. In this case, our function has a denominator, right? And there's a variable in the denominator. And so that tells us that what we need to be looking out for is that the denominator cannot equal 0. So the denominator cannot equal 0, because in that case, we would be dividing by 0, which yields an undefined answer. Okay, so once you kind of know what, in words, what that situation is, what you need to ensure, you can take that answer and translate it into either an inequality or an equation. So we're going to translate your answer to part 1 into either an equation. So this one we'll see is going to be an equation, but we'll see some other examples where it will be an inequality. Okay, so in this case, we said the denominator cannot equal 0. So the denominator was 3x minus 5, right? So we can say 3x minus 5 cannot equal 0. And so then we can just solve this equation. And so if you wanted to, you could leave this as an equal sign. I like to write it as does not equal just to really make sure that we know what we're doing, right? We're specifically trying to figure out what values of x are not allowed. And so I put the does not equal to really kind of make sure we're keeping that in mind the whole time. That being said, the way that you solve this will be exactly like a normal equation. So we can add 5 to both sides. So we have 3x cannot equal 5. Divide both sides by 3, and that means that x cannot equal 5/3. Okay, so that is basically our answer. And now really all that's left to do is to translate that into into interval notation. But before we go to interval notation, let's first write this on a number line. So we're going to graph your solution on a number line. So when I say graph it on a number line, basically what that means is that we want to shade a number line. We want to shade in the portion of the number line that corresponds to what we wrote down here. And so if what we wrote down here is that x cannot be equal to 5/3, well, that means we should shade everything else on the number line except for 5/3, right? Because the only restriction is that x cannot be 5/3. And so 5/3 is between 1 and 2. Just put a couple more numbers on here for context. So 5/3, right, is somewhere between, because 6/3 would be 2, 3/3 would be 1, so it's somewhere between the two. So I'll just kind of put it here. So this, let's say, is 5/3. And so what we're going to do is put an open circle on 5/3. An open circle represents the fact that, you know, we're basically trying to emphasize the fact that we're not shading, right? We're not shading at 5/3 because that's not allowed. But everything else on the number line, we want to make sure that that all gets shaded in. So next thing that we can do is, now that we have the number line, now we can translate the number line into interval notation. And you know, you might be able to skip the number line step, but I think, and we'll see some examples later on where I think the number line step is especially important. I think you're a lot more likely to get this part 4 correct if you do part 3, because it just gives you like a visual for which numbers you're actually talking about. Okay, so how does this go? Well, we see that we have two intervals, right? We have everything up to 5/3, not including 5/3. So that's -∞ to 5/3. And then we have everything from 5/3 onward. So it's basically like, you know, if it was all real numbers, it would be -∞ to +∞. It's basically like we just kind of plucked out that 1.5/3, and so we're left with these two intervals. And one more step, and I'm not going to do this on every example in this video just for the sake of kind of making the video not too long, but I think it's a really good idea to check your answer. And so what I mean by that, so let me write a little bit more here. So check your answer by plugging values into your original function. And so what I mean by that is, you know, let's not forget like the whole point of this question, right? The original question was to find the domain. So we're trying to find which numbers do and do not work in this function. And so a good way to test that your intervals are correct is to pick a number that is supposedly in the domain and plug it in. And if you plug in a number that is in the domain, you should get a defined answer. Then pick a number that is not in the domain and plug that in, and you should get an undefined answer. So what we figured out is that this interval here, all the numbers from -∞ up until 5/3, and then all the numbers from 5/3 to infinity, supposedly all of those numbers are in the domain. So let's just pick one number that is included here. And that's where actually I think the number line is helpful, because it can help you really see, okay, what's a number that is included here? So for example, 2 is supposedly in the domain, right? Because we see that it lies in the shaded part. So 2 should be in the domain. So let's check that. So let's see what we get when we plug in 2. So the original function was 2x over 3x minus 5. So we would get 2 times 2 over 3 times 2 minus 5. So that would be 4 over 6 minus 5. So that's 4 over 1. And that is fine, right? That is a defined number. And then in this case, there's really only one number that is not in the domain, right? The only number that's not in the domain is 5/3. And so that's really the only number that we can plug in to check not in the domain. Okay, so let's check that. So if we plug in 5/3, in the numerator, we're going to get 2 times 5/3 because the numerator was 2x. And then the denominator was 3 times x minus 5. So we have 3 times 5/3 minus 5. And so in the numerator, we're going to get 10 over 3. And then in the denominator, if you multiply 3 times 5 over 3, that becomes 5. So we have 5 minus 5. And so this simplifies to 10 over 3 over 0, which is undefined. I'll just say equals. Equal sign doesn't quite make sense here, but undefined is good, right? That's what we're looking for. So as I said, I'm not going to check the answer on every question in this, but I think a lot of students probably kind of skip over the checking step because it's like, oh, I probably have it right. I think not only does checking your answer help you get it right, but it also helps you understand. So I'm really going to be a big proponent of checking your answers all throughout this class, because if you check your answer and it's wrong, it might really actually help you see why it's wrong. And even in this case, I think maybe seeing like why this denominator came out to give you 0 is kind of insightful, right? You can see that 5/3 was the right choice because when you multiply it by 3, you get 5, and then you have 5 minus 5. So you can kind of see how the pieces fit together a little bit when you go and check your answer. Okay, so let's do some examples. All right, so next example we're going to do is we're going to find the domain. So I'm not going to write down find the domain because that's what we're doing on all of these. So I'll just say the function. So we have x squared plus 1 over x squared minus 4. So same deal as the last one, right? This is a function where we have variables in the denominator. And so what we need to do is ensure that the denominator is not equal to 0. So the denominator cannot be 0. And so how do we translate that into an equation? Well, that means that x squared minus 4 cannot be equal to 0. So from here, there's a couple different ways that you could solve this, but I think factoring is kind of the most illuminating way to solve this. So the left-hand side of this factors as what's called a difference of squares. So anytime you have something, and maybe I'll write this down as a note because this is something that's going to come up a lot in our class. So note, expressions of the form a squared minus b squared can be factored as a plus b times a minus b. And this is called a difference of squares. So basically, anytime you're trying to factor something where you have something squared minus something else squared, you can factor it as basically adding those two things together and multiplying that with subtracting. And the reason it works is that when you multiply them together, things cancel out. So maybe let's actually do that with this and actually show that it works. So here we have x squared minus 4. Well, that's the same thing as x squared minus 2 squared, right? 4 is a perfect square. And so that means that we can factor it as x plus 2 times x minus 2. And let's actually check that that's the correct factoring. So if we multiply these together, we end up with x squared minus 2x plus 2x minus 4. So what happens is that these middle terms just cancel out. And so we're left with x squared minus 4, which is exactly what we started with. So kind of a side note there, but as I mentioned, this is an important kind of factoring to be aware of. It'll definitely come up throughout this class. Okay, so we can factor this as x plus 2 times x minus 2 is not equal to 0. And so this is an important algebra fact about solving equations. So whenever you have a product, so things being multiplied together and they're equal to 0. And I know in this case it says does not equal 0, but it would be the same if it was equal to 0. So if you're multiplying two numbers together and you're getting 0, or in this case, not getting 0, what does that tell you about those numbers? Well, let's say this was just said equal to, just because it makes it a little easier to talk about. So if we're multiplying two numbers together and getting 0, the only way that is possible is if one of those two numbers is 0, right? Like the only way that you can multiply two numbers together and get 0 is if one of them is 0. And I would challenge you to come up with two numbers that you can multiply together and get 0 where neither of them is 0. It's not going to work. You're never going to find two numbers to multiply together to get 0 unless one of them is 0. And then the same thing holds if it's not equal, right? If we're saying two numbers are being multiplied together and the product is not 0, well, that means that neither of those numbers can be 0, right? Because then it would give you 0. Okay, so from here we can solve each of these. And so we get x is not equal to -2, and then we get x is not equal to +2. And so that is basically our domain, right? We now know that x can be any value except for negative and +2. So now all that's left to do is to translate this into interval notation. So let's go ahead and draw a number line. Just put a few numbers on here. Okay, so the numbers that we are excluding are -2 and +2, right? So it's this number here and this number here. And then everything else is fine. There's no issues with any other numbers. Okay, so now we can translate this into interval notation. So in this case, we have 3 intervals, right? So the first interval is everything from -∞ up until 2, not including 2, so I put a parenthesis. Or sorry, -2, my bad. Then we have everything from -2 up until +2. And then we have everything from 2 onward. And so this would be our final answer. And when this type of problem is given, I'd say the part that people most often miss is they'll somehow just kind of miss this middle interval. And that's why I think drawing a number line is really important, because then you'll see that there are clearly 3 intervals that need to be included. Okay, and as I said, I'm not going to check the answer, but you totally could. You could pick numbers from these intervals, plug them in. You should get something that is defined. But if you plug in 2 or -2, you'll get 0 in the denominator. So it will be undefined. All right, so let's do another one. So let's say that now we have h of x is equal to x squared minus 4. So basically same as the denominator that we had above. So every time I teach pre-calculus, a good portion of students, when we talk about domains, will just, for every function they get, they'll just start setting everything equal to 0. So I really want you to do this step of pausing and thinking about what type of function you have before you jump into anything. So in this, why was it that we did this step? Like, why did we set x squared minus 4 equal to 0? Well, we did it because x squared minus 4 is in the denominator, right? And we can't divide by 0, so you can't have x squared minus 4 in the denominator. Now, this function has no denominator, right? There's no fractions here at all. There's no square roots. So this is a function where basically nothing can go wrong. So nothing can make this function undefined. And really the reason for that is because, like I said, it has no square roots. It has no denominators with variables in it. And so there's like no issues with this function. And so basically that means that the domain is all real numbers. And how do you write all real numbers as an interval? Well, it's just -∞ to +∞, basically just saying, an entire interval of like the entire number line. Okay, so now we're going to jump into some examples involving square roots. And these, I think, definitely get a little bit trickier. Maybe not the first one, but as we go, some of these get a little trickier. All right, so let's say we have the function k of x is equal to the square root of 3 minus 9x. Okay, so let's go through those steps again. So the first step we want to do is figure out, what kind of function are we looking at here? What do we need to guarantee in order for this to be for this not to be undefined? Well, we know that when we have a square root, we cannot take the square root of a negative number. So you cannot, or I'll say it this way, the radicand, so remember the word radicand refers to the stuff under the square root. It cannot be negative. So how do we translate this into an equation or an inequality? Well, if you think about it, another way of saying cannot be negative is that it has to be greater than or equal to 0, right? Because anything that's less than 0 is negative, anything that's greater than 0 is positive, and then it is allowed to equal 0, right? You can take the square root of 0. You just can't take the square root of a negative number. So in this case, we say 3 minus 9x is greater than or equal to 0. And then we go and we solve this inequality. So you can do this a couple ways, and actually I'm going to show you 2 ways. So the way that I would probably do this is by adding 9x to both sides. So let me just mention quickly that solving inequalities is something that is meant to be a prerequisite for this class, and so that's why I'm not teaching this to you from scratch. I know you probably need some reminders, but just so you know, this is something that you should have learned in a previous math class, just like how to solve something that looks like this. Okay, so if we add 9x to both sides, we have 3 is greater than or equal to 9x. So now we can divide both sides by 9. So we get 3 over 9 is greater than or equal to x. And so 3 over 9 can be reduced. That's the same thing as 1/3. And so this is a fine answer, but typically you want to flip it the other way. So what I mean by that is there's 2 ways of saying this, right? 1 is greater than or equal to x is the same as saying x is less than or equal to 1/3, right? Those 2 statements are the same statement. And typically, at least for me, I have an easier time like understanding what it means to say x is less than or equal to 1/3 than I do, like I have trouble reading that and making sense of it, whereas this one I think is a little bit clearer to read. You could solve this a different way, and I just want to show it to you because it's an easy place to make a mistake. So you could do this by subtracting 3 from both sides. So you could have negative 9x is greater than or equal to negative 3. Then you would have to divide both sides not by positive 9, but by negative 9. And so when you divide both sides by a negative number, something important happens. So when you take an inequality and you divide or multiply both sides by a negative number, you have to flip the sign of the direction of the inequality. So if we divide both sides by negative 9, and I'll add a note about that flipping in a second, on the left-hand side we'll end up with x. On the right-hand side we'll have 3/9, right, because the negatives cancel each other out. And then this inequality sign has to flip direction. And so we end up with exactly the same answer that we got before. And then, as I said here, basically what happened is that when you have an inequality, if you're dividing or multiplying, in this case we were dividing, but same thing is true if you're multiplying by a negative number, you basically just have to flip the direction of the inequality sign. So less than or equal to becomes greater than or equal to, and vice versa. Okay, cool. So that's our answer. X is less than or equal to 1/3. And so now we just need to translate that into an interval. So put a few numbers on here, 0, 1, 2, -1, -2. So 1/3 is going to be somewhere between 0 and 1, so like here. And I'm shading it in because in this case, x can be equal to 1/3, right? It just has to be less than or equal to 1/3. And so I shaded it in, and then I'm shading to the left because we're talking about less than or equal to. And so how would we put this as an interval? Well, it would be the interval from -∞ up until 1/3, and then I put a bracket rather than a parenthesis because we're including 1/3. And so that would be our answer. Okay, so these next couple examples is where, or actually basically the rest of the examples in this video is where I think things get a little bit trickier. So just kind of heads up on that. Okay, so what did I just did k, so this next function let's call L of x. So this next function is the square root of 9 minus x squared. So the way that we start this out is exactly the same as the last problem, right? So the first thing we need to say is, okay, well, anytime we have a square root with a variable inside, we need to make sure that the radicand cannot be negative. And so in this case, that means that we take the inside, which is 9 minus x squared, and we say that has to be greater than or equal to 0. Okay, so where do we go from here? Well, there's a few different ways of solving this. You could factor the left-hand side as a difference of squares. I don't recommend that because it basically leads to a little bit of a more complicated situation because you're solving an inequality, not an equation. So factoring works really well for solving equations that are equal to 0. It doesn't work as well for inequalities. So what we're actually going to do instead is we're going to add x squared to both sides. Oops, kind of like what we did on the last one. So if we add x squared to both sides, we end up with this. And now I'm going to actually just kind of flip this around. So I'm just going to rewrite it as x squared is less than or equal to 9. So that's different from flipping the sign, right? All I'm doing is just rewriting it in the other order. Okay, so there is a way to solve this algebraically. I'm not going to show it to you because every single quarter I teach this, students do it wrong. I try so hard to really make the steps clear, and students just always get it wrong. Not always, but very often. So I think I'm gonna try to teach this to you a different way. So one really, really important thing that I want you to always keep in mind in this class, and actually let me pose this as a question for you to think about for a second. I want you to think about, what does it mean to solve an equation or an inequality? Like if someone asked you, someone just asked you, define solving an equation or solving an inequality, how would you explain to them what that means? So I think the best answer, you might have said something like doing algebra, dividing both sides, isolating x, blah, blah. Those are all okay answers, but the most general answer you can give is that solving an equation or an inequality just means finding the values that makes the equation or inequality true. Right? That's all it means. Solving an equation for x means finding the value of x that makes the equation true. Similarly, solving an inequality for x means finding the value or values of x that makes the equation true, or inequality true. So I'm going to write that down because that's kind of an important idea, I think. So solving an inequality or equation, at the end of the day, it really just means finding the value or values of x that makes the equation or inequality true. So the reason I'm saying this is that we don't need to do algebra to answer this question. We can kind of just think about what are the numbers that would make this true. So sometimes this means it is easier not to use algebra. Okay, so how would we kind of reason our way through this? So what does it mean to say x squared is less than or equal to 9? That means that we're looking for a number that when you square it, you get something that is less than or equal to 9. So let's start thinking of what are some examples of numbers that work, right? What's an example of a number that when you square it, you get something that's less than or equal to 9? So some answers that would work would be, might think of 0, right? If you square 0, you get 0, which is less than or equal to 9. X could be 1, right? 1 squared is 1, which is less than or equal to 9. X could be 2. 2 squared is 4, which is less than or equal to 9. X could be 3. 3 squared is less than or equal to 9, right? Because 3 squared is 9. Any bigger is not going to work, right? As soon as you go bigger than 3, it's not going to work because you'll get 16 or 25 or 36. Those numbers are all bigger than 9. So these are some answers that work, but X could also be negative, right? Because when you square a negative, it becomes positive. And so some answers that would work for negative numbers would be -1, -2, -3, right? Because as soon as you got like -4, well then that would, when you square it, you'd get 16 and that would be too big. So let's actually start to kind of put these on a number line, and that will help us figure out actually what our answer is. So we're kind of doing this one a little backwards. Instead of finding the solution and then doing the number line, we're going to do the number line first. Okay. And so another important thing to realize here is that not only are these answers true, but there's actually other numbers in between that would work as well, right? So like 1.5, if you square 1.5, because it's between 1 and 2, you'll get an answer that's between 1 squared and 2 squared. So it's not just, I'm not saying that these are the only solutions. I'm saying that these are some examples of solutions that we can use to kind of like figure out what the, where the answers lie on the number line. So maybe I'll make a note of that. These are some solutions, some numbers that work, right? Some numbers that when you square them, you get something that is less than or equal to 9. Okay, so where do these numbers lie? Well, we'll notice that the very biggest one is 3. And what's the very smallest one? It's -3. And then basically everything in between works, right? All the numbers that we listed out, they all lie between -3 and 3. So X can be anything between -3 and 3, including, like I said, decimals, fractions, any number that lies between -3 and 3. The important thing is that X cannot be bigger than 3 or smaller than -3, because then when you square it, you'll get something that is too big. Okay, so that's it. Now we can actually write this as an interval, right? We can say the answer is the interval from -3 to 3. So as I said, I'm not going to even show you how to do this with algebra because so many students get it wrong. You might guess, and I'll just show you that this doesn't give you all the answers. You might guess like, okay, well, I just take the square root of both sides and then I get X is less than or equal to 3. That would not be the correct answer, right? Because that would completely miss the fact that you have a cutoff at -3, right? If your answer was just X is less than or equal to 3, that would include things like -4, -5, -6, and those wouldn't work, right? Because when you square them, you would get something that's too big. So resist the urge to do algebra in these cases. Just kind of sit down and like pause for a moment and just like think about what numbers make sense. I think it's a way, I think easier and just kind of better approach for really understanding what's going on here. If you did solve it with algebra, basically you would have to use an absolute value and you'd have to remember how solving absolute value inequalities works. And that's just not something I really think is worth getting into for this sake. I think it's easy enough to figure it out with numbers. Okay, so this next one is going to seem really similar, but we'll see that in an important way it actually comes out differently. So instead of doing 9 minus x squared, now we have x squared minus 9. So it starts off the same. So first thing is that, again, we say, okay, we have a square root, so we have to make sure that the radicand, the step under the square root, cannot be negative. Okay, so in this case, that means x squared minus 9 has to be greater than or equal to 0, right? That's how we ensure that it's not negative. Okay, so now we can add 9 to both sides. So in this case, we have x squared is greater than or equal to 9. So how's that different from what we had here? Well, in this case, we had x squared is less than or equal to 9. This time we have x squared is greater than or equal to 9. And if you think about it, it's just because of the order of the subtraction in here, right? In this case, in order to make sure we get something positive or 0 inside the square root, this number needs to be bigger than the 9 that we're subtracting out. Okay, so again, rather than use algebra to solve this, let's actually think of some numbers that could work here. So what are some examples of numbers that when you square them, you get a result that is greater than or equal to 9? So 3 would work, right? If you take 3 and square it, you get 9, which is greater than or equal to 9. 2 would not work, right? If you take 2 and square it, you get 4, which is less than 9. But 4 would work because 4 squared is 16, which is greater than 9. 5 would work because 5 squared is 36, which is greater than 9. 6 would work, and so on. So basically, any number that is bigger than 3 is going to work. But that's not it. There's other answers that would work too, right? X could also be negative. So negative 3 would work because negative 3 squared is the same as positive 3 squared. Negative 4 would work. Negative 5 would work. Negative 6. So basically, any number that is less than negative 3. So let's sketch these on a number line and use that to come up with our final answer. So we have 0, 1, 2, 3, 4, 5, negative 1, negative 2. I always run out of space. Let me do this first. Negative 3, negative 4, negative 5. Okay. So again, let's start by just kind of doing the endpoint. So we see that x has to be at least 3 if it's positive, right? So we can put a point at 3, and then we don't want anything really to the left of 3 if we're looking at positive numbers. We only want things that are to the right of 3. So I'm going to shade on the right side. So that's where we get 4, 5, 6, etc. Now, if x is negative, then the biggest value it could possibly be is negative 3. And then what other numbers is it allowed to be? Well, it can be anything over here, anything to the left of negative 3. And so in this case, our answer is going to be 2 separate intervals. So we're going to have the interval from negative infinity up until negative 3 with a bracket. And then we'll also have the interval from 3 to infinity. Oops. And I guess let me say one more thing about these last two examples, which is, I know there's a lot of students, or maybe not a lot of students, but some students just really, really want to do it with algebra. And if you know the algebra and you can get it correct, then great. That's perfect. I just don't want to, I think there's enough kind of technicality involved in the algebra that I just think it's not really worth teaching that to you from scratch. If you do solve things like this using algebra, make sure you check your answer. I think that's kind of the best way of guaranteeing that you get the right thing. So make sure that after you get your answer, you test out some numbers to just make sure that you found the right intervals or interval. Okay, so a few more examples. All right, so next one I want to do is, what letter? I think maybe we're on N. So n of x is equal to, again, this is going to look very similar, but we'll see that's actually a bit different. So now we have x squared plus 9. Okay, so first thing, again, we can say that the radicand cannot be negative. That's always, if there's a square root, what we want to be thinking about. And so in this case, that means that x squared plus 9 has to be greater than or equal to 0. So at this stage, maybe pause and think about this statement for a second. So remember, I want you, when you see an inequality or an equation, don't think of it as a bunch of math symbols. Think of it as like a sentence, right? So this is a sentence that's saying a number squared plus 9 is greater than or equal to 0. So can you think of any numbers that would make this statement untrue? So can you think of any value of x that if you square that number and add it to 9, you get something that is not greater than or equal to 0? And there really aren't any numbers that work. So let's do one more step on this, and I think that will become even clearer. So if we subtract 9 from both sides, we get x squared is greater than or equal to -9. So remember that anytime you square a number, you always get a positive or result or possibly 0. And so you're never going to get a negative number. And so what that means is that this inequality is true for all values of x. So again, why is that? It's because there is no value of x. And I would challenge you, try to find it. Try a bunch of examples. Take different values of x, square them. You're never going to get a result that is less than -9. And so this statement is saying some number squared is greater than or equal to -9. That is always going to be true. Any number squared is going to be greater than or equal to -9 because it can't be negative, right? So it has to be greater than or equal to -9. And so if this is true for all values of x, what does that mean about the domain? That means that the domain is all real numbers. There's no value of x that's going to mess this up. And so to write all real numbers in interval notation, we've seen that that is -infinity to +infinity. And going back to the original equation, you can kind of see that, right? Like, think about this equation and think about plugging in different values of x. You're just never going to get a negative result under the square root. And again, if you don't believe me or you don't understand why I can say that with such, certainty, try some values of x and you'll see that it just will always give you a positive result under the square root. Okay, so 2 more examples, and both of these are going to be bring in something a little bit different. So let's call this next one p of x. So this time we have the function 3x to the 4th over the square root of 4 minus 2x. So what's different about this one? Well, in this case, we have kind of 2 different things going on, right? So in all the examples so far in this video, there's been either a square root or a fraction. And in this one, there's both. And so we have 2 different things we need to look out for. We need to make sure that 1, the stuff under the square root is not negative, but 2, we also need to make sure that the denominator is not equal to 0. So we have 2 things to kind of juggle here. So let's write those both down. So the radicand cannot be negative, but additionally, the denominator cannot be 0. So it turns out we can actually take both of these 2 sentences and write them as one inequality. So why is that? Well, the radicand cannot be negative basically means that 4 minus 2x has to be greater than or equal to 0, right? And then what would the denominator not being equal to 0 be? Well, if we want the entire denominator to be 0, that would mean that this stuff would be 0, right? Because the square root of 0 is 0. And so that means that 4 minus 2x cannot be 0. So how can we combine those 2 into one statement? Well, the first one is saying that 4 minus 2x is greater than or equal to 0. The second one is saying, actually, it turns out that 4 minus 2x is not equal to 0. And so the way we can combine them is just to say that 4 minus 2x has to be greater than 0 without the equal sign. So again, why does that work? It's because it makes the denominator, it makes sure that the denominator is not 0, right? If we don't have an equal sign, that's going to guarantee that the denominator does not equal 0. Furthermore, we need to make sure that this stuff is not negative. And so by saying it's greater than 0, that will also ensure that the radicand is not negative. And so now we can solve this. And we have 4 is greater than 2x. Divide both sides by 2, and we have 2 is greater than x. Another way of writing that would be x is less than 2. And so we can put that on a number line and then write it as an interval. Okay, so if x is less than 2, that means that x cannot be equal to 2, but it can be anything to the left of 2. And so in interval notation, this would give us negative infinity up until 2, not including 2. So we want to put a parenthesis. All right, so last example of this video, and this is probably the trickiest one. So let's say that we have the function q of x is equal to the square root of x minus 1 over x squared minus 4. So this is kind of like the last one in that we have two issues that we need to address. We need to address the fact that the radicand cannot be negative. And then we also need to address the fact that the denominator cannot be 0. So how is this different from the last one? Well, in the last one, the radicand and the denominator were kind of the same, right? That because the square root was in the denominator. In this case, they're different, right? The square root is in the numerator. And so this is actually going to give us two separate inequalities to solve. We're not going to be able to kind of combine them into one. Or I should say, one of them will be an inequality, one will be an equation. So what we're going to do is we're going to take each of these two things, write an equation or inequality and solve it. And then once we have all of those pieces, then we'll put them together on the number line and finally use that to write down interval notation. Okay, so if the radicand cannot be negative, so in this case, the stuff under the square root is x minus 1. So we're saying x minus 1 is greater than or equal to 0. So if we solve this for x, we get x is greater than or equal to 1. Okay, so that's our first piece. And then the second piece is that the denominator cannot be 0. And so that means x squared minus 4 is not equal to 0. We did this one earlier, right? This is the same denominator from earlier. We solved it by factoring. So we said x plus 2 times x minus 2 cannot be equal to 0. And so that meant that x plus 2 cannot be 0, and also that x minus 2 cannot be 0, because if one of those two things was 0, then you multiply them together, you get 0. And so this finally tells us that x cannot be negative 2 and x cannot be positive 2. Okay, so now let's take both of these pieces of information and graph them on a number line and kind of see how everything fits together. So we don't need too many numbers on here, but I'll just put a couple. All right, so let's start with the first one. So the first one tells us that x is greater than or equal to 1. And so that means that we're going to put an open circle on 1 and shade to the right of 1. Okay, so what does the second one tell us? Well, it tells us two things. It tells us that x cannot be equal to negative 2. And so that means that I'm going to put an open circle here. We'll see in a moment that I actually don't need that open circle, but I'm just going to put it there to kind of emphasize it. And then we also see that x cannot be equal to 2. And so that means that we need to make sure that 2 is not included here. So I'm going to put an open circle on 2. So why don't we actually need this open circle here? Well, so remember, the open circle is really just meant as a way to show that a number is not included. But we already know that everything over here is not included, right? Because the first inequality already told us that x has to be greater than or equal to 1. And so we don't really need this circle here, right? We can just kind of, I'll cross it out so that it's there in the notes. So this is unnecessary because we already know that x is greater than or equal to 1. So we don't need to worry about that. Basically, how can we kind of make sense of that? Well, like for example, if you tried to plug in -1 or 0, both numbers -1 or 0 would make the radicand negative, right? So we already know that nothing over here is going to work. So we don't even need to like add that extra information. However, we do need to add this information about x not being equal to 2, right? Because the inequality part, the part with the radicand, that would work with anything to the right of 1. So we do need to kind of add that extra piece of information that x cannot be equal to 2. So last thing we can do is rewrite this in interval notation. So there's going to be 2 intervals, right? So the first interval is going to go from 0, including 0, up until 2, or sorry, not 0. It's going to go from 1, including 1, up until 2, not including 2. And then the next interval is going to be everything from 2 onward. All right, so that is it. There's a worksheet for today that basically has, again, a bunch of problems pretty similar to the ones from this video. So I really recommend doing those just to get that practice and make sure you really understood everything from this video. I know this was a longer video. As I mentioned, the videos are going to vary a bit in length, but I think this is definitely on the longer side of what they will be. I will say that in general, videos like this where I do a lot of examples might end up being longer just because there is always the option to skip some of the examples or pause and do them yourself. So you don't need to watch every single example. All right, I'll see you all in the next video.